This is trigonometry, section 5.2, which is verifying trig identities. This is a fun one. I really like doing this one. It will rely a lot on your algebra skills and also us knowing those different trig identities that are kind of part of, we'll go over them, remind ourselves what they are, but we'll be using them throughout this. Just kind of, you'll realize there's not a lot of notes to go through. It really is just a lot of examples to make sure we have some practice with this. All right, so as we go through these different identities, remember there's a difference between a conditional equation where we're solving for x, right? I want to know what values of x satisfy this. So that's not what we're doing today. What we're going to do today is that we're trying to prove that something is an identity, that it works for any value of x that I plug in. For instance, our Pythagorean identity that says sine squared x plus cosine squared x equals 1, we can move kind of the cosine squared to the other side. So this is what we start with. And I say, okay, well, let me move the cosine squared over to the other side. And now I have basically a new identity. But we can show that it works for any value of x. For any angle that I plug into this equation, it will work for our original one, and then it will work for our new one. And all we've really done is we've used the understanding of algebra. If I subtract from one side of the equation, I have to subtract from the other. So that's a bit about what we're going to be doing today. So some guidelines, because students do often ask me, I'm stuck. I don't really know where to start. I don't really know what to do. So here are some good guidelines that your book offers, and I agree with a lot of these. So work with one side of the equation at a time. Start with the more complicated side. Start with the one that's more complex. Look for opportunities to factor, add fractions, square a binomial, or create a monomial denominator. So a monomial means just one term. We love just having one term in our denominator. So an example of a monomial, this is a monomial, whereas this is a binomial. And so we want to try to avoid having a binomial in our denominator. We want to have a monomial in our denominator. Look for opportunities to use those identities. The Pythagorean identities are going to be the ones that come up the most, but we're also going to need to know things like 1 over sine theta is equal to cosecant theta. So those will come up as well. Note that there are ones that pair nicely together. Sines and cosines pair well, secants and tangents pair well, and cosecants and cotangents pair well. If all else fails and you're really struggling, convert everything to sines and cosines. Always try something. Even if it leads to a dead end, it might give you some insight into the problem itself. Here's excuse me, our trigonometric identities that we'll need to use as we go through these. Like I said, the ones that we're going to use the most are really those reciprocal ones. The quotient ones, right, we need to know that tangent is sine over cosine, and these Pythagorean ones. We're not going to be using the cofunction identities during this section, or the even-odd identities, but you'll notice, right, we just keep building on this identities list. And yes, you will have these identities for the test. I don't think it's necessarily worth memorizing all of these. I'd rather make sure we know how to apply them. All right, so let's get started going through our examples. So over here on the left, right, we have a more complex side on the left-hand side rather than the right-hand side. So I am going to spend my time trying to simplify the left-hand side down and get out sine squared theta. Well, you'll notice I put our kind of Pythagorean identities up here in the corner because I see secant squared theta minus 1. And I want to know, is that equal to anything? Well, if I move a minus 1 over here, right, I get tan squared is equal to secant squared minus 1. So I can come back over here, and where I see the secant squared theta minus 1, I'm going to replace that with tan squared theta. So I have tan squared theta over secant squared theta. Now from here, maybe I want to think about, okay, can I get these maybe in terms of sine and cosine? So let's take tangent squared theta, which is sine squared theta over cosine squared theta, right? I'm kind of breaking this out. So there's my tangent, and I want to multiply by 1 over secant squared theta. Well, that's the same thing as saying cosine squared theta. My cosine squares are going to cancel out, and I wind up with sine squared theta, which is what I was looking for. So that is the first approach to doing this one. I'm going to go ahead and erase all of this and show you a completely different approach that will get us out the exact same answer. I want to start again with the left side because the left side is more complicated, but what I'm going to do, I'm going to break this down into two separate fractions, making sure that secant squared theta is the denominator for both. So I have secant squared theta over secant squared theta minus 1 over secant squared theta. Well, secant squared theta over secant squared theta, that's just 1, right? That's just a fraction with the number 1. And 1 over secant squared theta, well, that's cosine squared theta. Now, if I come back up to my Pythagorean identities and I say, well, if I move cosine squared over to the other side, I know that 1 minus cosine squared is equal to sine squared. So there, I've gone ahead and I've proven that the left side equals the right side. So I wanted to show you both approaches because a lot of these questions will have multiple ways that you can show or prove that these identities are true. Right, moving on to our next one, example 2. Which side's more complex? The right side. So we're going to start with that, and we're adding fractions. Now, in order to add fractions, we need a least common denominator. I need a 1 minus sine theta and a 1 plus sine theta. Now, let's go ahead and FOIL these. What do I get when I FOIL these out? Well, I get 1 minus sine squared theta. So that is going to be my least common denominator. And yes, I know you're probably already thinking, well, that's cosine squared. We'll get there, okay? But let's go ahead and add our fractions together to see what we wind up with. So my first fraction, that's missing the 1 plus sine theta. So I'm going to multiply both my numerator and my denominator by 1 plus sine theta. The other fraction is missing 1 minus sine theta. So I'm going to multiply by 1 minus sine theta over 1 minus sine theta. So I wind up with 1 plus sine theta over 1 minus sine squared theta plus 1 minus sine theta over 1 minus sine squared theta. When I add my fractions, I add my numerators, so those signs are going to cancel out, so I wind up with 2 over 1 minus sine squared theta. And here, right, you might be saying, okay, well, let's go ahead and replace 1 minus sine squared theta with cosine squared theta. So I wind up with 2 over cosine squared theta, which is 2 times 1 over cosine squared theta, and 1 over cosine is secant squared, so I get 2 secant squared theta, which is what I was trying to prove it was equal to. All right, let's look at our third example. All right, we got a lot going on over here, right? Notice, so the left-hand side looks more complex, so I'm going to start with those, but I notice right away that tan squared x plus 1, well, that's just going to be secant squared x. And cosine squared x minus 1, so if I subtract 1 and move this over, then I have to subtract the sine over. So I get cosine squared minus 1 is equal to negative sine squared. So I'm going to go ahead and replace this one here with negative sine squared x. And I'm trying to prove that that's equal, right, to negative tan squared x. But we've already pared it down a little bit, so that's looking pretty good to me. Secant squared is 1 over cosine squared. So I get negative sine squared x over cosine squared x. And since tangent is just sine over cosine, then this is equal to negative tangent squared x, which is what I was looking to accomplish. There we go. All right, example 4. We're going to verify each identity. This one is pretty straightforward. If you want to try to pause this and do this on your own, I would urge you to do that. So the left-hand side is more complicated. And what I want to do is, I don't see any squareds in there, right? I don't have a Pythagorean identity to use. So I'm going to replace tangent with sine over cosine. And then I'm going to replace cosecant with 1 over sine. So when I do that, right, my sines are going to go ahead and cancel out, so I get 1 over cosine, which is the same thing as secant x. So I wind up with the identity, or what I'm trying to prove there. All right, letter B. This actually comes directly from your last test, or not your last test. It was the 4.1 to 4.4 test. Do you remember that multiple choice question that I know a lot of us struggled on? So we're going to go ahead and do a very similar approach to what we did in the last example, where we're going to convert everything, and we're going to start with the left-hand side because it's a little bit more complex, just because we have tangent and cotangent and we're adding. And I know, is adding really that more challenging? Well, let's convert everything to sine and cosine. And when I do that, right, I notice I don't have a common denominator here because tangent and cotangent are going to have 2 different things in their denominators. So my least common denominator to add these 2 things together is cosine times sine. So this fraction over here is missing sine. This fraction over here is missing cosine. So I wind up with sine squared x plus cosine squared x all over sine times cosine. And we know sine squared x plus cosine squared x, well, that's just 1. So I wind up with 1 over the sine of x times the cosine of x, which is 1 over the sine of x times 1 over the cosine of x, which is cosecant x times secant x. And that's what I was trying to show, right? We need to rewrite it. Remember, when you multiply things, it is commutative. It does not matter. 2 times 3 is the same as 3 times 2. So we have gone ahead and proven that the left side equals the right side. All right, let's keep chugging along. We got example 5 here. We want to verify this identity. So a lot going on the right-hand side. And the reason being, we really don't like having this binomial here in our denominator. It makes things a bit more complicated. So we want to try to find a way to get it down to just a monomial, just one term. And what we're going to do is we're going to multiply by the conjugate of 1 minus sine x. And the conjugate is, you just take this exact same binomial, but change it to have a plus sign in between. And I'm hoping when we do this, all will be revealed why we are choosing to do this. So remember, I'm always allowed to multiply by the number 1, and all this is a fancy dressed up number 1 because my numerator and denominator are the same. Go ahead and FOIL your denominator. So when you FOIL your denominator, you're going to get out 1 minus sine squared theta, right? Because my outer and my inner terms are going to cancel out when I do that FOIL. In my numerator, I'm going to go ahead and distribute that cosine x through. And then in my denominator, the whole point, right, I was trying to get it to one monomial, just one term. Well, 1 minus sine squared x, that's just cosine squared x. And I got this whole mess up here in my numerator. So I'm going to bust up my numerator and write it as 2 separate fractions. So the cosine of x over the cosine squared x plus cosine x sine x over cosine squared x. Now remember, cosine squared x, that's just cosine x times cosine x. It's basically like x squared, right? X squared is equal to x times x. So I can break this down, right, as cosine x times cosine x. Okay. Which means this cosine x can cancel with that one. This cosine x can cancel with that one. So I'm left with 1 over cosine x plus sine of x over cosine of x. 1 over cosine of x is secant x. Sine over cosine is tangent. And lo and behold, we got down to what we were trying to prove, that the right-hand side is equal to secant x plus tangent x. All right, moving on. Example 6. Just a couple more examples to go. We have cotangent squared theta over 1 plus cosecant theta. So I want to work, I'm going to start by working with the left-hand side. I'm going to show you kind of a different approach because you might start simplifying one side and say, I just don't think I can simplify anymore. Well, then maybe we can go to the other side of the equation and simplify that as well. And as long as we get down to the exact same simplification, we're good to go. But I'm going to start with the left-hand side because it's got that binomial that we don't like. We don't like those two terms in our denominator. So I'm going to see what I can do here. Well, I've got a cotangent squared in my numerator, and I see over here that cotangent squared is going to be equal to cosecant squared minus 1. So I'm going to go ahead and replace cotangent squared with cosecant squared theta minus 1. Now, I don't know if you've realized this, but this is the difference of perfect squares. This can factor down as cosecant theta plus 1, cosecant theta minus 1, because this is basically the same thing as doing x squared minus 1, and how that can factor as x plus 1, x minus 1. So I've got that over 1 plus cosecant theta. Well, cosecant theta plus 1 and 1 plus cosecant theta are the exact same things. So the left-hand side has simplified down to cosecant theta minus 1. Now what I want to do is say, okay, I'm going to take the right-hand side and see if when I simplify this, I can get it down to cosecant theta minus 1. So I'm going to go ahead and break this down into two separate fractions. 1 over sine theta minus sine theta over sine theta. Well, 1 over sine theta, that's cosecant theta. Sine over sine is just this minus 1. So lo and behold, I do end up simplifying both the left and the right-hand sides down to the exact same thing. So that's another approach if you want to use that, showing that the identity on the left equals the identity on the right. That's the nice thing about algebra, okay? Remember, this is just using your algebraic skills, but using it with trigonometric identities. As long as you follow the rules of algebra, you will be good to go. All right, so here are some examples, calculus examples, they like to say. The main reason is we've got a higher power here, right? This is like we've got tangent to the fourth power, and powers of trig functions seem to pop up quite a bit in calculus. And so it's just being able to make sure you can factor, just like we would factor a higher order polynomial down in pre-calculus, can you factor a higher order, say, tangent down or cotangent or those things? Just don't be kind of afraid of it. Remember, we're just trying to prove that the left-hand side equals the right-hand side. And when I see the right-hand side, that looks more complicated to me. So I'm going to work with that and see if I can get the right-hand side to equal tangent to the fourth x. And remember, that just means we're doing tangent times tangent times tangent times tangent. On the right-hand side, I see we have a common factor between this binomial here of tangent squared x. So I'm going to factor out tangent squared x. When I do that, I'm left with tangent squared x times secant squared x minus 1. And if I come up here and I move over secant squared minus 1, I get that secant squared x minus 1 is just going to be equal to another tangent squared x. And when I multiply those two together, I get tangent fourth x. It's like multiplying x squared times x squared, you get x to the fourth. Same principles apply, but now it's tangent squared, or tangent to the fourth. There we go. Checked off. All right, our final example is a very, very, very similar. We've got kind of a lot going on the right-hand side. The left-hand side has a lot going on too. We got these higher order cosecant powers that we're working with here. But over here on the right, we've already taken out this common factor of cosecant squared, but I also notice I've got a cotangent in both of these too. So I'm going to factor out a cotangent x from this whole thing. So I get 1 plus cotangent, not cosine, cotangent squared x. Well, 1 plus cotangent squared x, 1 plus cotangent squared x is cosecant squared x. So I wind up with cosecant squared x times cotangent x times cosecant squared x. So all this really means is I can combine these two together, right? It's like having x squared times y times x squared. I'm allowed to multiply these together. So I get cosecant to the fourth x times cotangent x, and that's exactly what I was hoping to get to. So as you go through the homework, remember, it's okay to go down a path that does not necessarily lead to the right answer. Just give it a try. Use these identities. Use sine and cosine. Get a little bit creative. Some of these may appear to you as soon as you look at the problem, and others may take a few steps. Just don't give up. I promise you'll be able to do the exact same thing on your homework assignment.